Hello and welcome back to our discussion of reactions on a benzene ring. We've turned our attention now to making di-substituted benzene rings, and the last video was 5A, now we're on 5B. So again, after you watch all three of these, you should be able to do these problems from your chapter 18 problem set. So let's go ahead and get started with an example of a deactivating group. So just a reminder, I sent out this handout and it's also available in Learn, and it has a list of all of the activators up here and the deactivators down here. You'll see in the next video where I'll start distinguishing between strong, moderate, and weak. But for now, let's just keep it a little simpler and talk about activators versus deactivators. In the last video, you saw me do an example of an activator. So now we're going to turn our attention to a deactivating group. So let's take a look at a nitro group. So you know when deciding if a group is going to be activating or deactivating, we have to consider both the inductive effect and the resonance effect. So let's check that out for for this example. So the nitro group, since nitrogen, right, is a lot more electronegative than oxygen here, I've drawn in this bond dipole. So inductive effects, remember, happen through the sigma bonds only. So this is a single bond here, that's a sigma bond. So we expect the nitro group to withdraw electron density from the benzene ring. That's going to make it less nucleophilic, right? And so we expect from an inductive standpoint that the nitro group is going to be deactivating. So I'm going to say in the ring here, we've got a partial positive because we're sucking electron density away from the ring, making it again less nucleophilic. So we expect the nitro group to be deactivating. Let's check out from a resonance standpoint what we expect to see for the nitro group. So I've gone ahead and filled out one of the resonance hybrids here. So let's go ahead and draw the remaining resonance hybrids. Remember, you cannot move atoms when you draw resonance hybrids, so I've just filled in the atom skeletons, and now let's put in the non-bonding electrons and the multiple bonds. So what can we do here? So I can take a pair of electrons from the ring. If I move this pair of electrons here, the nitrogen can't have more than 4 bonds around it, so I'm going to push this up here. So what does that give me here? So now I have 3 sets of lone pairs on this oxygen. It has a formal -1 charge. This nitrogen now, we still have 4 bonds. This still has a formal +1 charge. This here has still 3 sets of lone pairs and a formal -1 charge. In the ring, we still have this and we still have this. So now notice here, this carbon just has 3 bonds. Remember, there's a hydrogen here. So this is our really an rhenium ion, okay? Remember that rhenium ion is a very specific type of carbocation. Okay, so notice here that we have a positive charge in the ring. So that means we're making the ring less nucleophilic. So again, from a resonance standpoint, we're going to expect the nitro group to be deactivating. Okay, let's continue to draw more resonance. I'm just going to use a different color here so we can see this. I'm going to take the pi bond and move it here towards that carbocation. All right, so now I'm going to have the double bond here. Now I'm going to have a formal plus charge here. This is still there. I still have the double bond here. I'm just going to swing that around there. Plus charge here. 3 sets of lone pairs, formal negative charge. 3 sets of lone pairs, formal negative charge. Remember, you can always do your check. So the net charge here was 0, right? And I still have a net charge of 0 here. I still have a net charge of 0 here. So that's always a good check when you're drawing these resonance structures where you end up with lots of charges, just to make sure that you haven't made a mistake. Okay, so let's continue on. Let's move this pi bond here. And when I do that, Then I have a plus charge here. Still have a double bond here, plus charge. And my lone pairs, negative charge. 3 sets of lone pairs, negative charge. Okay, and then I'm going to move this here. And when I do that, I can take down, doesn't matter which of these I use, I'll move that there. And now I have 2 sets of lone pairs here and a double bond. And I still have 3 sets of lone pairs here. And this is a single bond, and then this is double, single, double, single, double. Let's just do a check of our net charges. No charges here in the ring. I have a plus charge on this nitrogen, and I have a minus charge here, but still net charge of 0. So notice with the resonance hybrids, I've drawn out 5 here. And if you wanted to, you could draw some more where this oxygen has the double bond. But the point of doing this is to, once you see that there's a plus charge in the ring, that tells you that from a resonance effect standpoint, the nitro group is electron withdrawing, it's withdrawing electron density from the ring. And so the nitro group is also deactivating from a resonance standpoint as well. So these are both in agreement. So this is easy. The nitro group is deactivating. We find that if we take nitrobenzene and try to nitrate it, it is thousands of times less reactive than benzene. So let's take a look at what happens when we try to nitrate nitrobenzene, and let's look at the regio outcome. So if we take nitrobenzene and we force it to be nitrated, and again, this is a lot, this is like 10 to the 5 times less reactive towards this nitration than benzene. And that you don't have to memorize this number. I could ask you on an exam, is this more or less reactive than benzene? You would just tell me it's less reactive. You don't have to know that number. But let's look at if we are able to get this to react, what we end up seeing is that we don't end up with much of the ortho and the para product. We get primarily the meta product. So we want to be able to explain this regiochemical outcome. Why is it that with this deactivating group, when we nitrate it, we get mainly the reaction occurring at the meta position? So why is the meta product the dominant product? So the nitro group turns out to be, since we get mainly the meta, we say it's meta directing, and we already determined that it's a deactivator. So we can say it's a meta directing deactivator. So just like we did in the last video, we're going to assess the stability of each rhenium ion or sigma complex that leads to these different regiochemical outcomes, that for the ortho product, the meta product, and the para product. And that will be our clue for determining why we get mainly the meta. So let's go ahead and do this. So if I have ortho attack, what am I going to get? So again, these are all intermediates here. And let's see if I can redeem myself from my late night video, my previous video. We'll see. Okay, so if I'm using this pi bond to attack here so that I have this nitro group adding at the ortho position, just gonna flip that out there. So there's also a hydrogen here, remember, and then I have a formal +1 charge right here. And I'm gonna cringe a little bit. I'm actually gonna show this in red. And the reason I'm going to cringe a little bit is, remember that this nitrogen already has a plus charge on it. So let's put that down here somewhere. So if I have on my ring a plus charge. This is going to the nitrogen that already has a plus charge on it, right? This is extremely destabilizing to have two like charges next door to each other. Very, very unstable, okay? We know that like charges repel each other. So to push them right next to each other is extremely unstable. So this I expect right away to be a destabilized intermediate relative to any other intermediate that we get that doesn't have this plus charge right next door to another plus charge. Okay, let's continue. So I'm going to take a pi bond. I'll just show it in red so it's easier to see. And I'm going to move it over here. Keep all of the atoms in the same location. Draw on that H so you know it's there. So I've moved this here. So now the plus charge is here. Okay, let's keep going. So here, this is more stabilized relative to that, right? But remember with resonance hybrids, this is contributing to the overall intermediate. Okay, so let's move this then here. And we do that. So that's there. That means then my plus charge is here. Ooh, I'm gonna have to really cram this in. That's okay. NO2 and my H. NO2, then I have this right here. And so then I'm gonna go ahead and close this off and come up with my ortho product here. I'll fill in the double bonds in just a second. So remember, I'm just going to make this generic by saying B for base, pulling that off. And so this is going to move here. Okay. So I have this, this, and this, right? That's my ortho product. If I have meta attack, so that's at these positions. So let's say I'm using this pi bond here to attack. What do we get? So I've got my NO2. I have here the NO2 and there's a hydrogen. And then I'm going to have my plus charge here. And then I have this and this. Let's see if I can squeeze this in. I'm going to start off just filling in the atoms. NO2, NO2, H. Just set that up there. Okay, so I'm going to move this over here. And then I'm going to have my plus charge here. And then let's draw the other one. So far I don't have that plus charge at this carbon next door to the nitrogen with the plus charge on it, right? Okay, I'm going to move this here. And then my plus charge is here. Okay, so notice with meta attack, we don't see the plus charge at this position. Okay, so right away, I expect this rhenium ion intermediate, this sigma complex intermediate, to be lower in energy, more stable than that for ortho. And that means that the transition state leading to this is also stabilized. So we're gonna get to this faster than we would this. And then I'll go ahead and remove that proton and reestablish aromaticity there in the ring. There's our meta dinitrobenzene. Okay, and then let's do for para attack. Last set. Okay, so if I have I'm going to use this pi bond to attack. All right. And there's also a hydrogen there. Squeeze it in. My plus charge will be right here. And then I have this and this. Okay. Let's take the pi bond and move it towards the plus charge. So when I do that, I move this here. Then I have, again, cringing a little bit because two like charges next door to each other. Ouch, high in energy. So this is going to be destabilized relative to this. Okay, I'll just continue that. So if I have this here, then my plus charge is right here. Okay, let's rip off that proton, reestablish aromaticity. Here is our para product. Okay, so notice that I'm going to just kind of put boxes around the important structures here. So both of these structures here destabilize their intermediate. So both the para intermediate and the ortho intermediate are destabilized because of these resonance hybrids here. So this explains the regiochemical outcome that we see up here. Okay. So again, it's very, very unstable. To have like charges next door to each other. So let's take a look at what we see in the reaction energy diagram, what we would expect. I'm just going to the sigma complex, or the uranium ion intermediate here. So from our starting material, the ortho and the para, it doesn't matter. They're both higher in energy than the meta. That's the point. And you don't have to worry about if the para happens to be a little bit higher or lower than the ortho. There's more steric hindrance for the ortho versus the para, and that's why the ortho is a little bit higher than the para here. But it's the comparison of meta to these two that I want you to pay attention to. And then something that'll be really useful for you to kind of start burning into your brain is that most deactivators are meta directors. And the only exception that you have to know to this is that halogens are the exception. So we'll pick up with halogens in the next video. Stay tuned.